Welcome to today's deep dive. Imagine for a second, right, that you want to build a computer in your house to run your own private artificial intelligence.
Okay, a local setup.
Yeah, your first instinct, if you know anything about computers, is probably to look up how to build a high-end gaming PC, right?
Right. I mean, you buy a blazingly fast processor, throw in a ton of standard memory, and you just assume you're good to go.
Exactly. But if you do that today, in 2026, you will have just built a machine that is, well, functionally useless for AI.
Completely useless.
Because running an AI isn't like running a video game. It's actually much closer to organizing a really chaotic high-end restaurant kitchen. Like if you don't build a kitchen counter correctly, the whole restaurant crashes.
It completely upends, decades of conventional wisdom about what makes a computer fast. And what's even more fascinating is taking that same idea,
Yeah.
that upending of expectations, and applying it to an entire society.
Right, like the Finland study.
Yes. Think about Finland. A few years ago, they didn't just want to buy AI software from other countries. They wanted their citizens to actually understand it.
To know how it works under the hood.
Exactly. So they ran this massive social experiment where they successfully trained 1% of their entire national population, which is over 55,000 people.
Wow.
They trained them in the foundational mechanics of artificial intelligence, just to see how it would change their workforce and their civic landscape.
And those two ideas, right? The physical reality of that restaurant kitchen inside your computer and the societal reality of teaching an entire country how to think about algorithms. That's exactly why we're here today.
The core of it all.
Yeah, we're looking at a massive stack of sources today that cover the absolute foundations of AI as it exists right now. We've got a preliminary study from UNESCO on the ethics and global impact of AI, some cutting-edge local hardware guides from the DEV community, university-level data science roadmaps from Free Code Camp and Coursera, and real-world productivity frameworks from people like Jeff Su.
And our mission here isn't just to throw a bunch of technical manuals at you.
Definitely not.
Because in a world where you're bombarded with AI features in literally every app you open, the ultimate superpower is understanding the invisible mechanics underneath.
The why and the how.
Exactly. Like, why does a model hallucinate? Or why does your computer just crawl to a halt when you ask it a really long question? How do the people building these systems actually decide what's fair?
Right.
If you don't understand the physical infrastructure, the human education required, and the structural guardrails, you're essentially flying blind in the modern economy.
So let's cut through the buzzwords and start with the physical reality, the infrastructure. Because, people use terms like artificial intelligence, machine learning, and deep learning interchangeably all the time.
Yeah, as if they're just different marketing terms for the exact same software.
Right, but that's a fundamental misunderstanding, isn't it?
It really is. The best way to map this out is to visualize a set of concentric circles. The largest, outermost circle is artificial intelligence. That's the broadest umbrella.
Okay.
It's simply the concept of a machine exhibiting behavior that we, as humans, would consider smart. And that actually goes back decades.
Like when IBM's Deep Blue beat Garry Kasparov at chess back in 1997.
Exactly.
That was AI, but, it feels completely different from talking to a language model today.
Because it is. Deep Blue was what we call good old-fashioned AI, or symbolic AI. It didn't actually learn chess.
It didn't.
No. Human programmers spent years explicitly writing massive libraries of rules. They coded opening moves, endgame scenarios, and these brute force evaluation algorithms.
So if Kasparov does X, calculate every possible Y and choose the one with the highest mathematical advantage.
Exactly. It was just a phenomenally fast rule follower operating inside a perfectly closed, predictable universe. A chessboard is a pristine environment.
Right, but the real world is definitely not pristine.
Not at all. You can't write an explicit rule for every possible way a human being might phrase a sarcastic email.
Or every weird lighting condition a self-driving car might encounter at a stop sign.
Right. Which forces us into the second concentric circle, which is machine learning. Instead of giving the computer the rules, you give it the data.
Oh, okay.
You feed an algorithm 1,000,000 pictures of stop signs, and it analyzes the pixels to find its own patterns. It figures out the rules of what a stop sign looks like based on the examples you gave it.
And then inside that circle, we have the innermost core, right? The one driving the massive 2026 boom, deep learning.
Yes. Deep learning uses artificial neural networks. These are algorithms layered on top of each other, which is where the word deep comes from, loosely inspired by how neurons connect in the human brain.
So it's mimicking our biology, sort of.
Very loosely, yeah. Data passes through this web non-linearly. It allows the computer to take wildly unstructured data, like a chaotic audio recording or a huge block of text, and identify incredibly complex, abstract correlations.
But the trade-off for that power, according to our sources, is that deep learning requires a staggering, almost incomprehensible amount of data and physical compute power to actually function.
And that physical compute power is where things get really interesting.
Which brings us right back to the restaurant kitchen. I was reading Nicholas Turzashvili's hardware guide on the DEV community for building a local AI machine, and the architectural shift he describes is wild.
It really changes how you look at a computer.
Yeah, because if you're playing a video game, you care about the GPU, the graphics processing unit, pushing out frames as fast as possible. You want the chip to process instructions at lightning speed. But for AI, speed is secondary to space.
Right. The processing speed is practically irrelevant if the model can't fit into the active memory.
Exactly. So let's build the kitchen for you. In a computer running a large language model, your GPU chip is the chef. The processing speed is simply how fast the chef's hands can chop the vegetables.
Okay, I like this.
Now, the regular system RAM on your motherboard, the 32 or 64 gigabytes you may have, that's the pantry down the hall. It can hold a lot of ingredients, but it's far away.
But the critical component here isn't the pantry, it's the video RAM, the VRAM.
Yes, the memory physically soldered onto the graphics card itself right next to the processor. In our restaurant analogy, the VRAM is the kitchen counter.
And why does the size of that specific counter dictate everything?
Because of how large language models work. Let's say you download a 7B model. That means the model has 7 billion parameters. Think of a parameter as a tiny calibrated knob or dial that the AI uses to weigh the relationship between words.
Like a 7 billion parameter model is basically a recipe with 7 billion intricate steps.
Exactly. And when you ask that model a question, the chef cannot run down the hall to the pantry to check step number 4 billion, run back, chop an onion, and then run back down the hall for step 4 billion and 1.
That would take forever.
The entire recipe must sit on the kitchen counter simultaneously. Every single parameter has to be loaded into the VRAM at once for the model to generate text efficiently.
And a 7B model takes up about 5 gigabytes of VRAM just to exist on that counter.
Right. And if you want to run a massive 70 billion parameter model, that recipe takes up roughly 40 gigabytes of counter space. If your graphics card only has 8 gigabytes of VRAM, the recipe physically spills over the edge of the counter.
And what happens then?
The system panics. It forces the chef to start using the pantry down the hall, and your generation speed drops from a fluid 40 words a second to maybe 1 or 2 words a second. The machine basically freezes.
It becomes unusable.
Mm-hmm.
But the model itself isn't the only thing taking up space on that counter, is it?
Mm.
We have to consider the context window.
Oh man, the dishes problem. This was honestly the most illuminating part of the hardware guide for me. When you talk to an AI, it has to remember what you said earlier in the conversation to give you a coherent answer.
Right. It needs short-term memory.
Yeah, and that memory is called the context window. Every prompt you type, every paragraph it generates, takes up physical space in the VRAM. It's literally like dirty dishes piling up on the kitchen counter right next to the massive recipe book.
So if you buy a graphics card with exactly enough VRAM to hold just the model, you have zero room for the dishes.
The second you say hello, you run out of counter space, the dishes crash to the floor, and the chef has to run to the pantry again.
Which is why the hardware tiers in 2026 are so incredibly specific.
Exactly. The DEV Community Guide points out that a starter AI machine, maybe in the $1,500 range, relies on the NVIDIA RTX 4060 Ti, but it comes in 2 versions, 8 gigabytes and 16 gigabytes.
And if you buy the 8 gigabyte version, because it's cheaper,
you are dead in the water. You must have that 16 gigabyte counter space to run a 7B model and still have room for the conversational dishes.
And what about for power users? The ones who want to run those massive 32 billion parameter models that start rivaling the cloud.
They're hunting the secondary market for used RTX 3090s.
An older card.
Yeah, it's older, so the chef's hands are a little slower, but it has a massive 24 gigabytes of VRAM. It's all about the counter space, not the speed.
You know, it's worth bringing up the Apple Silicon architecture here because it takes a completely different approach to the kitchen.
Oh, right, the M-series chips.
Yeah, the M-series chips in modern Macs use unified memory.
They basically knocked down the wall between the kitchen and the pantry, right?
Essentially, yes. The GPU and the CPU share the exact same pool of memory. So if you buy a Mac Studio with 128 gigabytes of unified memory, your VRAM is functionally 128 gigabytes.
That's a massive counter.
Huge. Now, The processor itself might not be quite as specialized for AI rendering as a dedicated NVIDIA Tensor Core, so the chef chops a bit slower. But the counter space is so vast that you can load 70 billion parameter models locally.
Which is nearly impossible on standard consumer PC hardware without linking multiple really expensive graphics cards together. But this raises a really practical question, I think. Building these local machines is expensive and complicated. Why bother? I mean, I can just open a browser and use a Frontier model in the cloud for free or for like 20 bucks a month.
It comes down to the difference between a home gym and a commercial gym.
Oh, okay. I like that. Expand on that.
Think about it. A local AI running on your own hardware is your home gym. The equipment might not be the absolute most advanced in the world, but it's yours.
Right.
You have total privacy. Your data never leaves your hard drive. There are no API subscription costs, no downtime if your internet goes out, and crucially, nobody is logging your sensitive corporate documents to train future models.
So you do 80% of your daily maintenance work there.
Exactly. But when you need to deadlift 600 pounds,
You go downtown to the commercial gym, the
Oh.
cloud.
you use the cloud for the bleeding-edge reasoning, the massive data synthesis that requires models with trillions of parameters. But we have to look critically at what that commercial gym actually is.
Right. The UNESCO preliminary study really forces us to pull back from the consumer perspective here and look at the macro reality of the cloud. It's not an ethereal, invisible thing.
Not at all. The cloud is a hyper-industrialized physical infrastructure.
It's massive windowless concrete buildings sitting on sovereign land, consuming just rivers of water and oceans of electricity.
Precisely. And this is where the physical reality of AI meets global geopolitics. To build a single massive data center requires extensive mining for rare earth elements, things like neodymium and yttrium.
And the fabrication of the silicon chips themselves requires ultra-pure water.
Right. And then there's the energy consumption. Training just one of these frontier models takes months and consumes enough megawatt hours to power a small city.
Yeah, I was reading about how the cooling systems alone in some of these data centers are causing localized water stress in certain municipalities.
And that's just the creation and operation phase. Then you have the hardware life cycle. Because this technology is advancing at such an unprecedented pace, the compute hardware becomes obsolete incredibly fast.
So a massive server rack might be outdated in 3 years.
Exactly. And this is contributing to a staggering e-waste crisis.
And let me guess, the multinational corporations based in wealthy nations that are reaping the economic benefits of the AI aren't the ones processing the toxic e-waste.
The UNESCO report points out exactly that. Developing nations often end up as the dumping grounds for this electronic waste. They bear the environmental burden, the heavy metals leaching into their soil and water, without actually having access to the computational power that generated the waste in the first place.
Wow.
The physical toll of the cloud exacerbates existing global inequalities.
Let me push this a step further because the geopolitical implications here seem massive. For the entire 20th century, global power dynamics were largely dictated by who controlled the oil, right?
Yes, absolutely.
If you had the oil or controlled the shipping lanes for the oil, you had a seat at the table. If the absolute best AI, the systems that will discover new pharmaceuticals, optimize national energy grids, or predict economic markets, if they require these massive multi-billion-dollar server farms, are we just swapping the old oil monopolies for new silicon and data monopolies?
It's arguably a more concentrated monopoly than oil ever was.
Really?
Think about it. Oil is geographically distributed across several continents. The capacity to design sub-nanometer silicon chips, secure the rare earth supply chains, and build 50-gigawatt data centers. That's currently concentrated in the hands of a few multinational corporations and a couple of superpowers.
Right.
A developing nation might have brilliant engineers, but if they lack the reliable national electricity grid to power a supercomputer, or the capital to buy the chips, they are structurally locked out of the highest tiers of the new digital economy.
They become permanently dependent on renting compute power from foreign corporations.
Exactly. They don't own the kitchen counter, so they can never cook their own meals.
That's a perfect way to frame it. However, while that infrastructure dictates the raw capacity of what AI can do globally, having the biggest supercomputer is kind of useless if nobody knows what to type into the terminal, right?
Which is a huge point. Many sociologists argue that the true bottleneck for society isn't silicon. It's human capital, the literacy required to actually command these systems.
Which moves us beautifully into our next area of focus, education. The
Huh.
human element, because there are two distinct sides to this coin. There's the challenge of how humans learn to build and direct AI, and then there's the reality of how we use AI to learn everything else.
Let's start with human literacy. How do you prepare a population for a technological shift this massive?
Yeah.
The Finland case study we mentioned at the start is honestly the perfect blueprint.
Right, the elements of AI initiative. Finland looked at the landscape and realized that AI was going to touch every industry: healthcare, logistics, education, agriculture.
It's unavoidable.
So they decided that AI literacy could no longer be treated as a specialized niche just for computer science majors at the University of Helsinki. It had to be a fundamental civic skill, like basic math or reading comprehension.
So they set that audacious goal.
Yeah.
Teach 1% of their entire population the foundational mechanics of artificial intelligence.
And they partnered with universities and private companies to create this free, highly accessible online curriculum. They didn't focus on teaching people how to code in Python, right? They focused on the concepts.
Yes. What is a neural network? What is training data? What is algorithmic bias?
And the response was incredible. They easily surpassed their 1% goal. Over 2 million students globally eventually took the course. But the demographic breakdown is what really caught my eye in the source material.
It's fascinating.
Around 40% of the participants in Finland were women.
Which is a profound data point, considering that female participation in traditional computer science and engineering programs often hovers around 20%.
So why do you think that happened? Why did this specific course break through that demographic barrier?
Because it reframed the technology. When you present AI strictly as advanced mathematics and back-end software engineering, it often suffers from the same exclusionary cultural filters that plague STEM fields globally.
Right.
But by framing AI as a civic tool, something that impacts your daily life, your job, your privacy, it becomes immediately relevant. Demystifying the technology removes the intimidation factor.
It empowers people.
Exactly. It empowers people to realize they don't need a PhD in statistics to understand how their data is being used
Yeah.
or to command an AI tool effectively in their own workplace.
But let's say someone listening to this deep dive does want to go all the way.
Okay.
They don't just want the civic literacy. They want to be a data scientist. They want to build the models. I spent a lot of time looking at the 2026 curriculum roadmaps from Coursera and Free Code Camp. And I have to be honest, the barrier to entry for the hard skills is formidable.
It is. It is an incredibly mathematically rigorous discipline. Machine learning is not magic. It's applied statistics and multivariable calculus executing at an unimaginable scale.
The Free Code Camp roadmap breaks down the math you absolutely must know to understand what's happening under the hood. First up is linear algebra. We're talking about vectors, matrices, and tensors.
To give that some physical reality, a scalar is just a single number, say the number 5. A vector is a list of numbers. You can visualize it as an arrow pointing to a specific coordinate in space.
Okay.
A matrix is a two-dimensional grid of numbers, like a spreadsheet. But a tensor is an n-dimensional grid of numbers.
Wait, why do we need n-dimensional grids?
Think about processing a high-resolution color photograph. You don't just have height and width. You have a red color channel, a green color channel, and a blue color channel, each with different intensity values for every single pixel.
Right, it's layered.
Exactly. To feed that image into a neural network, you have to represent it as a massive, multi-dimensional mathematical object, a tensor. This is why the specialized chips Google uses in their data centers are literally called tensor processing units. They're hardware built specifically to crunch massive grids of numbers.
Okay, so that's the data structure. But then the roadmap gets into calculus, specifically differential calculus, partial derivatives, and a concept that seems to be the engine of all machine learning: gradient descent.
Gradient descent is how an AI actually learns.
Explain how that works. Break down the mechanics of the learning process for us.
All right, imagine you're dropped on the top of a very rugged, mountainous terrain. It's pitch black, extremely foggy, and you're wearing a blindfold. Your singular goal is to find the absolute lowest point in the valley. How do you do it?
I guess I would feel the ground with my feet, figure out which direction slants downward, and take a step that way.
Exactly. You feel the slope, and you step down. Then you feel the slope again, and take another step. You repeat this iteratively until the ground is perfectly flat in every direction. You've found the bottom.
Okay, I follow.
In machine learning, the mountain represents the error rate of the AI model. When it starts out, its predictions are terrible. It's at the high peak of the mountain. It uses calculus, specifically partial derivatives, to measure the slope of its own errors.
It figures out how wrong it is.
Yes. It then adjusts its internal parameters, taking a step down the mountain, recalculates, and adjusts again. It is mathematically seeking the lowest possible error rate. That is gradient descent.
That is a brilliant way to visualize it. So you've got linear algebra for the data, calculus to minimize the errors, and then the guide goes heavily into statistics. Bayes' theorem, probability distributions, and information theory, specifically Shannon entropy.
Shannon entropy is vital. It measures the amount of uncertainty or surprise in a piece of information.
Like trying to guess the next word in a sentence.
Exactly. If I say, I am going to take the dog to Zoom,
Yeah.
your brain has very low uncertainty about the next word. It's almost certainly walk. The entropy is low.
Right.
But if I say, my favorite thing in the world is, the entropy is incredibly high. It could be pizza, jazz, sleeping, or skydiving. Large language models use information theory to calculate the exact probability distribution of what the next word should be based on the context.
And once you master all of this math, you still have to actually write the code to execute it. The Coursera roadmap highlights the programming languages. Python remains the absolute king of AI development because it's highly readable and has massive pre-built libraries like PyTorch and TensorFlow, but it's not the only player.
No, Python is excellent for building and testing models, but it's an interpreted language, which means it can be relatively slow when executing in the real world.
Right. If you're coding the computer vision system for an autonomous vehicle traveling 70 miles an hour down a highway, milliseconds matter. You don't use Python for that.
You use C++mint.
Yeah. It's much harder to learn, the syntax is unforgiving, and it requires vastly more lines of code, but it compiles directly to the hardware and is blazingly fast. Then you have Java, which is heavily favored in massive enterprise environments for its security and stability.
And Julia, which is fascinating. It's a newer language built specifically for data science that attempts to combine the execution speed of C++ with the user-friendly syntax of Python.
But look, I have to stop us here, because I'm looking at this terrifying multi-year roadmap of multivariate calculus, tensor mathematics, and C++ syntax, and I'm looking at the calendar. It's 2026.
Yeah.
If I want to build a data scraper or automate a workflow or even build a lightweight app, do I really need to spend 3 years learning partial derivatives if I can just open a window, talk to a frontier AI model in plain English, and have it write the Python code for me in 12 seconds?
You've just articulated the central tension in modern software development.
Right.
The barrier to entry for utilizing code has effectively dropped to zero. We've shifted from an era where humans translate their intentions into machine syntax to an era where the machine translates human intention into syntax for us.
Which brings us to a YouTube productivity tutorial we analyzed from Jeff Su. He introduces a concept that perfectly captures this shift. Vibe coding.
Vibe coding is such a wonderfully evocative term. It completely changes the paradigm of how we interact with software.
Jeff argues that for the vast majority of people, the 90% of us who aren't trying to build a new foundational neural network from scratch, but just want to apply AI to our daily jobs, the old way of talking to AI is completely dead. Like, a few years ago, we were all obsessed with prompt engineering.
Yes, the dark art of trying to trick the AI into giving you a good answer.
Exactly. You'd spend 15 minutes writing these elaborate, highly structured paragraphs, act as a senior marketing executive with 20 years of experience in the automotive industry, output your response in a table with 4 columns, adopt a professional but slightly witty tone, do not use the words synergy or innovative.
We had to micromanage the older models because they lacked robust reasoning. If you didn't fence them in with extreme precision, they'd wander off and hallucinate or give you generic, unusable corporate speak.
But in 2026, Jeff points out that prompting is dead. Context is king. The frontier models are so advanced at reasoning that you don't need to tell them how to act. You just need to show them the environment. He outlines the OC framework, outcome plus context.
Let's roleplay that. Walk through exactly how the OC framework changes a daily task.
Okay, let's say I want the AI to design a 4-day-a-week workout plan for me. The old prompt engineering way would be me typing. Act as an elite personal trainer. I am a 35-year-old who wants to build muscle. I only have 45 minutes a day. Give me a push-pull legs routine. Ensure the volume isn't too high.
And what did you get?
The AI will spit out a generic list of exercises it's scraped from a million fitness blogs.
It's functional, but mediocre.
Right. The 2026 vibe coding way using the OC framework is entirely different. First, I establish the context. I don't describe what I want the routine to look like. Instead, I go online and find a highly specific, science-based article written by an actual biomechanics expert detailing the exact physiological principles of a push-pull hypertrophy routine.
Yeah.
I copy the entire text of that article and paste it into the AI. That is my context. I am grounding the model in expert data.
You're building a temporary, highly specialized knowledge base.
Exactly. Then I give it a simple one-sentence outcome. Based strictly on the principles in this article, generate a 4-day workout plan for someone who has 45 minutes a day to train.
The difference in the output is staggering, isn't it?
It's night and day. Because the AI isn't relying on its general homogenized training data, it's synthesizing the specific gravity, tone, and expertise of the context you provided.
It infers the necessary volume, the rest periods, and the exercise selection directly from the biomechanics article. You didn't have to explain how to be an expert, you just handed it the expertise.
Jeff emphasizes that the single best piece of context you can ever give an AI is an example of what good looks like. If you wanted to draft a project update email to your boss, don't spend 5 minutes describing your boss's communication style.
To show it.
Yeah, just copy and paste the last 3 project updates your boss actually approved, paste in your bullet points for this week, and say, draft this week's update using the exact structural format and tone of these examples. It works flawlessly.
What this illustrates is a massive pivot in the human skill set. Memorizing exact syntax or command structures is becoming obsolete. The premium human skill in the AI era is curation, the ability to identify high-quality context, clearly define an outcome, and critically evaluate the result.
And this methodology is evolving beyond single chat windows. Jeff dives into what happens when you start linking these interactions together into AI systems, features like Google's Gemini Gems or Anthropic's Claude projects.
This is where we move from a tool you use once to an environment you collaborate in continuously.
Let's use the Claude projects example. A project is a permanent, persistent workspace dedicated to one specific area of your life or job. You can upload massive amounts of background knowledge into it. Jeff talks about creating a health checkup project.
Right.
He uploads his annual blood test results, his doctor's notes, his resting heart rate data from his smartwatch. That project retains that memory indefinitely.
And in isolation, that's useful. You can ask it to graph your cholesterol over 3 years. But the real power of an AI system is interconnectivity.
Yes, an AI system can act as an overarching intelligence that sits above your individual projects and cross-references them. Jeff gives a hypothetical where the overarching system looks at his health checkup project and then looks at his workout coach project.
And it notices a connection.
Exactly. The system notices a contradiction. It flags him and says, hey, your recent blood work shows a spike in LDL cholesterol, but your current workout project is entirely focused on heavy weightlifting with 0 cardiovascular work. I am going to automatically suggest integrating 20 minutes of zone 2 cardio on your rest days.
That is the holy grail of what AI can achieve. Spotting obscure patterns across totally siloed data sets. A human being might never mentally connect the spreadsheet from their doctor with the notepad app they use at the gym. But the system sees the entire board.
It's an incredible level of personalization, but it also represents a massive transfer of trust.
A huge transfer.
If we are utilizing AI to write our code, curate our health regimens, and manage our professional communications, we're leaning heavily on its judgment. This is why the UNESCO studies section on how AI is transforming formal education is so critical. We're starting to trust AI to shape how the next generation learns.
The potential for positive disruption in education is enormous. We have to look at the X5G1 project highlighted in the UNESCO text. It stands for the Cross-Modal, Cross-Cultural, Cross-Lingual Global Open Educational Resources Network.
That is a very long acronym. Break down what it actually does.
Open Educational Resources, or OER, are free, high-quality learning materials available online. University lectures, textbooks, research papers. The problem with online education has never been a lack of material. The problem is discoverability and relevance.
Right, like if I search for a physics lecture on YouTube, the algorithm just shows me whatever video has the most views, which is usually a generic Western-centric university lecture in English.
Precisely. Search algorithms default to the mean. They optimize for popularity. But the X5G1 project uses AI to actively fight that homogenization. It models the specific cultural, linguistic, and educational context of the individual learner, and then surfaces material that matches that context, regardless of where it originated.
Give me a practical example of how that changes a classroom.
Imagine a high school science teacher in a rural part of East Africa looking for materials to explain agricultural biology. A standard search engine gives her a lecture from MIT about industrial farming in the American Midwest.
Which is scientifically accurate but culturally disconnected from her students' lived reality.
Exactly. But the X5G on AI, understanding her geographic and cultural context, might instead translate and surface a brilliant lecture from an Indian university about sustainable farming in arid climates, or a resource incorporating indigenous agricultural knowledge that perfectly aligns with the local ecosystem.
It connects the student with the most relevant knowledge on Earth, even if it's buried under 1,000 hours of more popular Western content. It actively breaks the echo chamber of traditional search.
It does. It has the power to democratize education in a way we've never seen. But
That is always a but.
But as we pivot into the implications of this, we have to confront a deeply unsettling reality. If we are trusting these systems to curate our children's education, to analyze our health data, and to parse our job applications, how do we know their decisions are fair?
Which brings us to the most philosophically challenging and arguably the most vital part of this deep dive, the ethics of AI. Because if you peel back the slick interfaces and the helpful chatbots, you find structural issues that can do real harm.
To understand the root of the ethical danger, we have to look at a concept the UNESCO report calls performance without awareness.
I found this concept chilling when I read it. Explain what performance without awareness actually means in practice.
Let's go back to games. Not chess this time, but Go, the ancient board game that is exponentially more complex than chess. When the AI system AlphaGo defeated Lee Sedol, one of the greatest human players in history, it executed moves that were so profoundly creative, so alien to human strategy, that commentators literally wept.
It demonstrated a level of strategic mastery that humans hadn't achieved in 3,000 years of playing the game.
It performed at an absolute genius level.
It did, but AlphaGo does not know what the game of Go is.
Exactly. It doesn't know it's playing a game. It doesn't know what a board is or what a human opponent is. It feels no pressure, no joy of victory, no fear of making a mistake. It possesses zero conscious experience. It is merely a sprawling web of tensor mathematics calculating probability distributions. It performs flawlessly, but it is completely hollow inside. It has zero awareness.
So why is that a danger to us?
Because human beings are biologically and socially hardwired to associate high performance with consciousness and authority. When we encounter an entity that speaks to us with perfect grammar, writes beautiful poetry, or executes brilliant strategic maneuvers, we instinctively project a mind onto it. We anthropomorphize the machine.
We assume that because it sounds smart, it must understand what it's saying.
Exactly. And because we project this mind onto it, we grant it unearned trust. We assume it possesses an objective, rational perspective. But the sources are incredibly clear about this. There is no such thing as truly objective data. AI is only as unbiased as the data it is trained on. And human history is essentially a catalog of biased data.
We have to talk about the Amazon hiring tool here because it's the textbook example of how this goes wrong.
It perfectly illustrates the danger of assuming data is objective.
Amazon wanted to automate their resume screening process. They wanted an AI to look at incoming resumes and pick out the absolute top-tier talent. So they fed the AI 10 years worth of historical resumes from people Amazon had successfully hired in the past.
Right. The logic was, look at our best people, figure out what they have in common, and find more of them.
But the flaw was in the historical data. Because the tech industry has historically been heavily male-dominated, the vast majority of the resumes in that 10-year training data set belonged to men.
So what did the AI do? The programmers didn't write a line of code saying, do not hire women.
Yeah.
They didn't explicitly program sexism into the machine.
Right.
But the deep learning algorithm looked at the billions of data points and found a massive statistical correlation. It essentially learned the mathematical rule. Being male correlates strongly with being hired at Amazon.
And because the machine has performance without awareness, it didn't understand the societal context behind that data. It didn't know about the gender gap in STEM fields. It just saw a mathematical pattern and ruthlessly optimized for it.
It started actively downgrading any resume that contained the word women's. If a candidate wrote that they were the captain of the women's chess club, the AI penalized their score. It literally taught itself to replicate the historical bias.
In data science, this is known as overfitting, right?
The model fits the training data so perfectly that it captures all the noise, the errors, and the societal biases embedded within it. It takes a historical human flaw and codifies it into a mathematical rule. And because that rule comes from a computer, human HR departments might initially look at the results and think, well, the computer ran the numbers. This must be an objective, mathematically poor meritocracy.
But the stakes are relatively low there compared to what happens when AI enters the public sector. The UNESCO report extensively covers a tool deployed in Pennsylvania called the Allegheny Family Screening Tool, or AFST.
This is a critical case study. And what's fascinating about the Allegheny Family Screening Tool isn't a political angle about who is right or wrong in local government, but the sheer mechanics of data collection and how structural data sets physically shape outcomes.
Right. The goal of the tool was completely well-intentioned. The county wanted to use data analytics to predict the likelihood of child abuse and neglect so they could deploy social workers more effectively and protect vulnerable kids.
But the algorithm requires data to make predictions. And child abuse is incredibly difficult to measure directly and accurately across an entire population. People don't self-report it. So the system had to rely on proxy data.
Explain what proxy data is in this context.
It's data that you use to infer something else. The algorithm looked at variables that were tracked in county databases, interactions with child welfare services, reliance on public housing, juvenile justice records, and calls to hotlines.
And this is where the structural mechanics of the data set create a massive blind spot. The source notes that if a wealthy family is struggling with substance abuse or domestic issues, they typically utilize private resources. They go to private therapists, check into private rehab facilities, use private doctors. None of those interactions are logged in the county's public welfare databases.
Exactly. But poor and working class families rely on public services for their safety net. When they access healthcare, food assistance, or counseling, it generates a data point in the county system.
So the training data that the AI is looking at is drastically skewed. It oversamples poor families simply because they generate more public data.
Yes. The algorithm, performing complex statistics on this uneven data, essentially learned to conflate poverty with a high risk of child abuse. The source material argues that because the proxy data was inherently class-based, the AI created a system that structurally targeted and disadvantaged poor working families. It ended up punishing poverty rather than accurately predicting abuse across the whole socioeconomic spectrum.
The algorithm wasn't malicious. It was just blindly optimizing the flawed data it was fed.
Flawed data creates flawed AI. Which brings us back to the human element, the people building these systems. The UNESCO text talks about the leaky pipeline problem in the tech industry.
This is a critical factor in why these biases go unnoticed, isn't it?
It is. The leaky pipeline refers to the attrition of diverse talent in the tech sector. For example, the report notes that female participation drops by roughly 40% between university graduation and executive leadership roles.
Why does that matter for the code, though?
Because the humans who select the training data, define the outcome metrics, and test the models are the ones who determine what correct looks like. If the room of engineers building a facial recognition system consists entirely of one specific demographic, they might not realize that the system fails miserably at recognizing faces of people from other demographics.
They aren't intentionally being exclusionary.
Right, they just literally don't have the varied lived experiences in the room to spot the blind spots. When the creators do not reflect the diversity of the real world, the AI will not serve the real world fairly.
And this extends far beyond algorithms for hiring or social services. It's bleeding deeply into culture and art. Let's talk about the next Rembrandt project.
A fascinating collision of technology and art history.
Researchers took 346 of Rembrandt's original paintings and fed them into a deep learning model. The AI analyzed everything: the geometry of the faces, the exact thickness of the brushstrokes, his use of shadow and light, his typical subject matter. And then the AI generated a brand new original painting. They used a 3D printer to physically print it with layers of paint to perfectly mimic Rembrandt's texture.
It is, by all visual accounts, a beautiful painting that looks exactly like a lost Rembrandt. But it creates an absolute nightmare for copyright law and the concept of authorship.
Because who is the author? Is it the software engineer who wrote the neural network? Is it the person who typed the final prompt? Is the algorithm itself the creator? Or is it Rembrandt, since his entire life's work constituted the training data?
Our current legal frameworks are completely unequipped to answer this. If we grant copyright to the AI, we fundamentally devalue human creativity. We elevate a mathematical equation to the status of a human artist. But if we say there is no copyright at all because a machine generated it, how do we protect the intellectual property of the original artists?
This is the massive debate happening right now with generative AI. Companies are scraping billions of copyrighted images and text from the internet without compensation to train models that can then instantly mimic the style of those exact human creators.
If we do not establish fair frameworks for how training data is sourced and compensated, we risk the deliberate exploitation of human artists and the potential collapse of the creative economy as we know it.
And the cultural impact goes even deeper when you look at language. Language is the ultimate expression of human culture. And the UNESCO report highlights a profound duality in how AI interacts with language. On one hand, it's performing miracles of preservation.
The Australian Indigenous Language Project is a prime example of that. Researchers had amassed 50,000 hours of recorded audio of Indigenous languages. To have human linguists listen to, transcribe, and catalog that amount of tape would have taken an estimated 2 million hours of labor.
It was a mathematically impossible task for humans.
But by utilizing AI models specialized in audio processing, they analyzed the tape in a fraction of the time. They successfully modeled and preserved 12 highly endangered Indigenous languages, including Creole and Warlpiri. It's an incredible victory for cultural preservation.
It's beautiful, but the duality is that the very nature of natural language processing, how computers understand words, forces human language into rigid mathematical boxes.
Yes, computers do not understand meaning. They understand numbers. To process human language, AI translates our messy, emotional, context-heavy words into formal languages, which are strict mathematical structures.
And what gets lost in that translation?
Everything that makes language human: irony, cultural connotation, poetry, the subtle shift in tone that changes the entire meaning of a sentence. Mathematics cannot perfectly capture nuance. Furthermore, to train a language model effectively, you need a massive data set. The internet contains oceans of data in English, Mandarin, and Spanish. It contains very little data in Swahili, Icelandic, or Warlpiri.
So the frontier models work phenomenally well in English and terribly in less dominant languages.
Which creates a systemic ethical risk. If access to the most powerful economic and educational tools in the world requires fluency in English, AI will drastically accelerate English-centric homogenization. It forces the world to abandon local languages and cultural nuances just to interact with modern infrastructure.
And speaking of interacting with infrastructure, we cannot have a serious discussion about the ethics of algorithms without talking about the AI we all interact with every single day. Social media algorithms.
The curation algorithms running our news feeds are perhaps the most pervasive and psychologically impactful AI systems ever deployed.
And we have to ask, what is the outcome they are optimized for? They aren't optimized to tell you the truth. They're optimized for engagement, time on device, keeping your eyeballs on the screen so they can serve you in another ad.
And psychological data shows us exactly what drives engagement: emotional resonance, specifically validation and outrage.
The algorithms learn very quickly that if they show you an article that confirms everything you already believe, you will click like. If they show you an article that enrages you and demonizes a group you disagree with, you will leave a massive angry comment. Both actions equal engagement.
This mathematical optimization naturally creates filter bubbles and echo chambers. The algorithm actively hides opposing viewpoints or nuanced discussion because nuance doesn't trigger the dopamine or adrenaline required to keep you scrolling.
You end up living in a customized reality where it feels like everyone agrees with you and anyone who doesn't is an absolute extremist.
And when you combine that algorithmic isolation with generative AI, bad actors using AI to instantly generate millions of fake news articles, hyper-realistic deep fakes of politicians saying things they never said, or deploying automated bot networks tailored to exploit the specific psychological profiles of individual voters.
Like we saw the beginnings of in the Cambridge Analytica scandal, but exponentially more powerful.
Exactly. It threatens the very foundation of the democratic process. Democracy relies on a shared set of basic facts to function. If our algorithms are feeding us entirely different, mathematically isolated realities, civil discussion becomes literally impossible. We lose the ability to govern ourselves.
Okay, let's take a breath. We have covered a staggering amount of ground. We have a severe VRAM shortage on our physical kitchen counters, massive environmental impacts from data centers, steep mathematical barriers to entry for engineers, algorithms that inadvertently punish poverty, the potential collapse of copyright, the homogenization of global language, and the algorithmic erosion of democracy.
It's a weighty list.
It is. Which brings us to our final focus: synthesis and the future outlook. We need to tie the infrastructure, the education, and the ethics together to see where this is all heading. Because these aren't just theoretical problems happening inside a chat window on your phone. AI is rapidly moving into the physical world, making decisions where the stakes are literally life and death.
The transition from AI as an advisory tool to AI as a high-stakes decision maker is the most critical threshold we're crossing. Let's look at healthcare. Watson for Oncology is a prime example.
Right, this is the system trained to assist doctors in diagnosing and treating cancer. It can ingest and cross-reference thousands of newly published medical journals, clinical trial results, and patient histories in milliseconds. It provides an incredible synthesis of data that no human doctor could possibly keep up with.
It frees up the doctor's time and offers brilliant, data-driven treatment recommendations, but it introduces the black docs problem.
What happens when the AI's recommendation contradicts the intuition of a human doctor who has practiced for 30 years?
It creates a profound crisis of medical authority. Because it is a deep learning neural network, the AI cannot explicitly explain why it reached its conclusion in a linear way that the human doctor can verify. It simply outputs a statistical probability based on billion-parameter correlations that are invisible to the human eye. It says treatment A has an 87% chance of success.
So the doctor's trapped. If the doctor ignores the AI, relies on their own experience, and the patient tragically dies, is the doctor legally liable for ignoring the machine?
And conversely, if the doctor follows the machine's recommendation against their own better judgment and the patient dies, who is to blame? You cannot put an algorithm on trial for malpractice. The integration of high-level AI forces us to fundamentally renegotiate liability, authority, and trust in professional fields.
And those stakes escalate exponentially when we look at national security. The UNESCO report dedicates a significant section to AI in the military and peace building. It makes it very clear that the military application of AI isn't just about building smarter drones or autonomous tanks. It's fundamentally redefining the concept of what armed force even means.
The true revolutionary potential of military AI lies in situational awareness and the speed of cyber warfare. Imagine an overarching AI system analyzing real-time satellite imagery, global financial markets, social media sentiment across a continent, and logistical shipping data, all simultaneously. It could predict social instability, resource riots, or enemy troop movements weeks before they happen.
It sounds like the precogs from Minority Report, predicting the future based on massive data correlations.
But the immediate danger isn't just prediction, it's the speed of execution. In the realm of cyber warfare, an AI can constantly probe an adversary's national energy grid or banking system, detect a vulnerability, and launch an autonomous, highly complex cyber attack at a speed that humans physically cannot react to.
The human chain of command is too slow.
Way too slow. If one nation deploys an autonomous AI defense system that operates in milliseconds, adversary nations have absolutely no choice but to deploy their own autonomous systems just to compete.
It creates a completely automated arms race.
Yes. And the speed of that automated interaction could be globally destabilizing. Imagine a scenario where a military AI misinterprets a faulty sensor reading. Maybe it sees a strange weather pattern or a flock of birds and identifies it as an incoming threat. It could launch a preemptive cyber or kinetic strike in a fraction of a second, triggering an automated retaliation from the enemy's AI, escalating a false alarm into a global conflict before a single human leader is even awake to say, wait, stop. It's just a glitch.
So how on earth do we stop that? How do we build guardrails when the technology is moving so fast that we can barely comprehend it, let alone legislate it?
The UNESCO text synthesizes a primary foundational solution, and it comes back to how we educate the people building the systems. It's a framework called Ethically Aligned Design, or EAD.
Okay, ethically aligned design, how does that change the process?
Historically, if you go to an engineering school, you're taught to optimize for three things: speed, efficiency, and computational power. You build the fastest, most powerful machine possible, and you leave the moral implications to the sociologists and the lawyers to figure out later. Ethically aligned design argues that this approach is no longer survivable. We must teach our engineers to explicitly design for human values like privacy, fairness, and transparency from the very first line of code. Ethics cannot be a software patch you download after the system is already deployed. It has to be baked into the architectural mathematics.
I need a tangible example of that. How do you bake ethics into math?
Let's use privacy by design. Imagine a city wants to build an AI camera system to estimate the size of a crowd at a political protest to ensure they deploy enough medical support.
Okay. The standard way to do that would be to set up high-resolution cameras, record all the video, run it through a facial recognition algorithm, count all the unique faces, and store the data.
which creates a massive, searchable surveillance database of citizens exercising their right to protest, severely violating their privacy.
Right.
Under ethically aligned design, the engineer approaches the problem completely differently. They write the code so that the camera itself pre-processes the image at the physical source. The sensor strips away all high-resolution details and extracts only the geometric contours, just the abstract outlines of human shapes. The AI counts the outlines perfectly, achieving the goal of crowd estimation, but the system is mathematically incapable of recording, transmitting, or storing a single recognizable human face.
The privacy protection isn't a policy, it's baked directly into the physics of the system.
Exactly. It's an engineering solution to a human rights problem. But to achieve that, you need a workforce of engineers who are educated in sociology, ethics, and civic responsibility, not just tensor mathematics and C++.
So I want to turn this directly to you, the listener. We have covered a staggering amount of ground today in our deep dive. You now understand why you need a massive VRAM kitchen counter to run your local AI and why the dishes piling up will crash your system. You know the math behind gradient descent. You know how to abandon prompt engineering and use the OC framework for vibe coding. And you understand the profound structural dangers of algorithmic bias, proxy data, and systems that perform with absolute brilliance but possess zero awareness. So what does this all actually mean for you tomorrow morning when you open your laptop? Are we simply destined to be guided by machines that outcompute us?
The answer lies entirely in how we choose to engage with these systems on a daily basis. The ultimate defense against the pitfalls of AI isn't a better algorithm and is not waiting for perfect legislation. The ultimate defense is human critical thinking. We must cultivate a societal habit of relentless questioning. We must never accept an AI's conclusion automatically, whether it's a medical diagnosis, a suggested workout routine, a filtered news feed, or a block of generated code. We have to demand transparency, understand the context of the data, and actively retain our human agency in the loop.
Which leaves us with a final lingering thought to chew on. If artificial intelligence is rapidly evolving into the ultimate answer engine, a system capable of ingesting all the world's data to give you a statistically perfect response to any query, then perhaps the future doesn't belong to the people who know the most facts, because the machine will always know more facts.
That is a profound shift in how we measure human value.
Exactly. If algorithms can seamlessly mimic our logic, emulate our creativity, and even perfectly synthesize our voices, then the most valuable trait you can cultivate going forward is your uniquely human conscious experience. It is your ability to experience the world, to feel the friction of reality, and to ask the profound, unpredictable questions that no mathematical model would ever think to ask. That lived experience, that messy, beautiful awareness is the one thing a machine, no matter how massive its VRAM kitchen counter is, can never simulate. Thank you for joining us on this deep dive. Keep questioning the algorithms in your own life today.